Hello, welcome to my channel. Here we are discussing questions for the topic electricity for Edexcel AS Physics level examination, and that too from the past 4 to 5 years of Edexcel board exam question paper questions. Before we start, please like and share my videos and also subscribe to my channel so that you can get notification about my new videos. In fact, these videos are good for other exam boards also, since almost all exam boards include questions from the topic electricity. In fact, this is a second part of the series, and I shall show you how to answer these questions. So let's start with question number 9. First 8 questions are solved in part 1 of the series. So this is starting from question number 9. A student sets up the circuit shown in the 3 identical lamps and switch. Each lamp is marked 1.5 volt and two 1.5 volt cells of negligible internal resistance are used as the power supply. The 2 lamps labeled A and B with the normal brightness when the switch is open. Explain what will happen to the brightness of each lamp when the switch is closed. Here you can see that the 2 resistors or 2 lamps A and C, they are connected parallel, and to this parallel combination B is connected in series. So this is one loop A and C, they are parallel, and this parallel combination is connected in series with the bulb or the lamp B. So when we are writing the total resistance, so the total resistance of the circuit will be resistance of A parallel C plus resistance of B. So when the switch S is closed, this will be the total resistance. So let's start writing the answer. Here in the loop, A and C are connected parallel. A and C are connected parallel. And B is connected in series to this loop of A and C. So when we are writing the total resistance of the circuit when the switch is closed, so these are all when the switch S is closed. So the total resistance of circuit is the resistance of lamps A and C parallel plus the resistance of bulb B. So this is the total resistance. So since A and C are connected parallel, the resistance of R A parallel C decreases. So the total resistance decreases. So when the total resistance decreases, the current of the circuit, this is increasing. That is, the circuit current is same as the current flowing through lamp P. So if I mark this as the circuit current, I circuit, total circuit current, the same current I will be flowing through lamp B. So the total circuit current increases means current passing through B also increases. And you can see that the circuit current is shared between A and C, and current is shared by A and C in the loop, the parallel loop. So we can say that the current flowing through the lamp B, which is the same as the total circuit current, which is greater than the current flowing through A and current flowing through C. The current flowing through A and the current flowing through C. So it is current flowing through C. Because in A and C, the current is shared. They are identical lamps, therefore current in A will be same as current in C, which is less than current through B, which is the main circuit current itself. So from this we can say brightness of lamp brightness of A, sorry, not A, brightness of B greater than brightness of A, which is same as brightness of C. So this is what is happening. So since A and C are connected parallel and B is connected in series to the loop, the total resistance, when the switch is closed, the total resistance will be the resistance of the loop plus the resistance of B. So I can write when switch is closed, when switch is closed, resistance of A parallel C decreases. That means the total resistance decreases, the circuit current increases, or the current flowing through lamp B increases, and current is shared by A and C in the loop. We can see current through B greater than current through A, which is same as current through C. Therefore, brightness of lamp B will be greater than brightness of A, which is same as brightness of C. Now let us move on to the next part of the question. Sketch a diagram such a current potential difference graph for a filament lamp on the axis given. So let us take current here, the voltage here. Similarly, current and the negative voltage. Sketch a current potential difference graph. So the graph will be initially current and voltages are proportional and then it decreases. You will get a symmetrical graph to the negative axis. It will be this way. So this is the current and potential difference graph for the filament lamp. Explain the shape of this graph in terms of electron movement through the lattice. Electron movement through the lattice. So as you see, initially when the PD increases, that means the voltage increases, current is increasing. As a result, the temperature increases due to heating effect of current. Okay, so let us write it step by step. So we can write initially as voltage increases, I increases. This voltage only we call it as potential difference PD. As voltage increases, current increases. Now due to heating effect, of current, temperature of the filament increases. Temperature of the filament increases. Okay. Then, as temperature increases, what is happening? The vibrations of the lattice ions or atoms increases. So when temperature increases, the vibrations. Of lattice ions or lattice atoms increases. Therefore, the collision rate between electrons and between the electrons and the vibrating ions or atoms increases. So the collision rate between electrons increases, but here they are asking the movement through the lattice. So let us write, so the collision rate of electrons and vibrating ions or atoms increases. So this causes an increase in the resistance, or we can say it causes an increase in the resistance in the sense it causes uh, a decrease in the rate of increase of current. This causes a decrease in the rate of increase of current. So rate of increase of current decreases means the resistance increases. The resistance increases, or in another way we say that the increase in PD is at a greater rate than the increase in current. See, here we have seen this causes a decrease in the rate of increase of current. A decrease in the rate of increase of current means the increase in PD is at a greater rate than current. That is, the increase in PD is at a greater rate. than current. This is the reason for this particular shape of the graph. Initially, current and voltage are increasing, but due to the heating effect, the temperature increases. As the temperature increases, the vibration of lattice ions increases. So the collision of electrons with the vibrating ions, lattice ions or atoms increases. This causes a decrease in the rate of increase of current. So increase in PD is at a greater rate than current. Now the next question is, a copper wire of radius 0.4 millimeter carries a current of 5.1 ampere. Calculate the drift velocity of the electrons in the wire and the number of charge carriers per meter cube of copper. It is also given. A copper wire of radius 40 millimeter. So we have to convert the radius to meter. So radius equals 40 millimeter, which is the prefix for milli is 10 to the power of negative 3, this much meters. This is a radius. Calculate the drift velocity of the electrons. Calculate the drift velocity of the electrons. So the equation for the drift velocity I, or equation for the current in terms of drift velocity, I equals N Q V A. Here we have to calculate the drift velocity, therefore writing as the subject I over NQ A, and we are substituting the values. There is a current of 5.1 ampere. So the current is 5.1 over the number density is given. So N equals, this is the number density, N, and the current is 5.1. So it is 8.5 times 10 to the power of 28 times the charge of the electron, which is 1.6 10 to the power of minus 19 times. Now A, we know what is the value of A, and for a wire which is in the form of a cylinder, area is pi times r square, which is pi times the radius is 40 times 10 to the power of negative 3 the whole square. So I am putting same number here, pi times 40 into 10 to the power of negative 3 the whole square. Together we can calculate. Substituting all the values together, and on calculation that is giving a value of 7.5 times 10 to the power of negative 4 meter per seconds. This is the drift velocity. It's a direct question. Now moving on to the next question, a student investigates how light intensity affects the resistance of a light dependent resistor LDR. She sets up a circuit using a cell with a negligible internal resistance as shown. So here a student investigated how light intensity affects the resistance of a light dependent resistor LDR. So there is an LDR shown here. She sets up a circuit using cell with a negligible internal resistance. The EMF of the cell was given. So let us mark everything here. The EMF is given as 1.5 volt. This is the LDR. Then the voltmeter reading is 1.19 volt. So if we are calling this as the fixed resistor R, this is the voltage across the fixed resistor, which is 1.19 volt. Calculate the resistance of the LDR when the lights were off. That is, LDR is not shown, light on LDR. That is the meaning. So the EMF is provided, the voltage across the resistor is provided. So from this, what we can calculate is the voltage across the LDR, because this is a series circuit. So in a series circuit, the supplied voltage is shared among the components. So this is, let us call it as, this is the resistance of the, or voltage of the LDR across the resistance or across the LDR. It is the voltage of the LDR. So the total EMF, which is the sum of the voltage of the load resistor or resistor plus it is the voltage of the LDR. So we can find out what is the voltage of the LDR, which is E minus VR, and E is given as 1.5 minus 1.19, and on calculation we are getting it as 0.31 volts. This is the voltage across the LDR. Now the question is, calculate the resistance of the LDR. Now here the current flowing through the circuit we can calculate. That is, suppose I is the current starting from the battery. The same current is flowing through the resistor R. So same current I. So here the resistance of fixed resistor and voltage of the fixed resistor both are known. Therefore, we can calculate the circuit current I, which is same as the current flowing through the resistor according to Ohm's law. It is the voltage across the resistor over its resistance, and the voltage across the resistor is 1.19 over the resistance value. What is the resistance value? Resistance value is 5 kilo ohms. So 5 kilo means multiplying with 1000, so 5000. So on calculation, we are getting a current of 2.38 times 10 to the power of negative 4 amps. This is the circuit current or current passing through the resistor. Since the LDR and resistor are connected in series, okay, since LDR in parallel to connected parallel to the fixed resistor, I of the resistor is same as I passing through the LDR, which is 2.38 times 10 to the power of, times 10 to the power of negative 4 amps. So now we know what is the, see here it is the voltage of the LDR, which is 0.31, and now we know what is the current through the LDR, which is this much. So now we know both the voltage and current, so we can calculate the voltage of the LDR is current through the LDR times the resistance of the LDR. So that is, from this we can find out the resistance of the LDR as voltage of the LDR over the current of the LDR, which is the voltage of the LDR is 0.31 over 2.38 times 10 to the power of negative 4 Please make use of your calculator. On calculation, this is giving an answer of 1300 ohms. So this is the resistance of the LDR. Resistance of the LDR is 1300 ohms. So we calculated what is the voltage of the LDR. Then we calculated the current flowing through the resistor, which is same as the current. So both are in series, not parallel. Both of them are connected in series. So the same current is flowing. Now let's move on to the next part of the question. When the lights were switched back on, the student discovered that it was impossible to calculate the resistance of the LDR using the circuit. The teacher said that the lights on, the resistance of the LDR was about 9 ohms. The question is, explain why the student was unable to use the circuit to determine the resistance of the LDR with the lights on. And the resolution of the voltmeter was 0.01. So here, when the lights on, LDR resistance is 9 ohms. So with that resistance, let us see what is the total resistance. So R total, this is when lights on. So I'll write when lights on, R total is R plus R of LDR which is giving you an answer of 5000 plus 9. So it is 5009 ohms. This is the total resistance. Therefore, we can calculate what is the circuit current. The circuit current is the EMF, which is 1.5 over 5009. On calculation, it is giving a current of 2.99 times 10 to the power of negative 4 amps. This is the total circuit current. From this we can calculate what is the drop across the resistor when the switch or when the lights on. So drop across the resistor is current of the resistor, which is same as the circuit current, times R. This is giving an answer of current through the resistor is 2.99 times 10 to the power of minus 4 times the resistance value is 5000. So this is giving an answer of 1.495 volts. This is the the voltage through the resistor. So as you know the voltage through the resistor, now we can calculate. So I'm writing it here. Therefore, the voltage drop across the LDR, which is the total voltage EMF 1.5 minus the drop across the resistor, because these two are connected in series. Therefore, that resistor is coming as a very, very small value, 0.5 volts. You can see that the drop across the LDR is very, very small, and it says that the resolution of the voltmeter is 0.01. So this voltage drop across LDR is very small compared to 0.01 the resolution. So the voltage drop across LDR cannot be measured. So voltage of the LDR cannot be measured using this voltmeter. And the meaning of resolution is how accurately or how fine a voltmeter can take the measurement. How accurately or how fine a voltmeter can measure the or can take the measurement. This is the meaning of resolution. So here the resolution is 0.01 volt, which is slightly greater than the LDR voltage, or LDR voltage is more compared to the resolution. So LDR voltage cannot be measured using the given voltmeter. Let's answer the next question. The graph shows how the current I varies with the potential difference V for a filament bulb and a negative temperature coefficient thermistor. So two graphs are given. One is for the filament bulb and the other one for is the thermistor, which is a negative temperature coefficient component. So as you know, the negative temperature coefficient means its resistance is having a inverse relation with the, not a direct relation, it's an inversely proportional to the temperature. This is the meaning of negative temperature coefficient. The first part is actually it's a repeated answer only because we have answered the question 2 or 3 questions back. We have answered this part explaining the shape of this graph. So in this, and that too they want the explanation of the graph in terms of the movement of the, it's given here in terms of the movement of the conduction electrons in each component. So let us answer for a filament lamp. So for the filament lamp, as you see, so let us answer filament lamp first. So in the filament lamp, what is happening is, you see here as the initially as the voltage increases, the current is also increasing initially. Okay, so let's put it as an answer initially. As voltage, that means PD. PD increases, I increases. And this increase in I is having, or current flow is having a heating effect. So due to the result of heating effect of current, the temperature increases. Due to heating effect. Due to heating effect of current, temperature increases. Temperature in the filament, temperature of the filament increases. So now what is happening as the temperature increases? As temperature increases, the vibration of the lattice ions or atoms increases. As temperature increases, the vibration of lattice ions or atoms increases. So when this vibration of the lattice ions increases, it is difficult for the conduction electrons to flow through or move through the lattice ions, because as the vibration of the lattice ions increases, the collision rate, the rate of collision of the electrons with this oscillating ions or atoms increases. So as the vibration of lattice ions increases, what is happening? So the collision rate, rate of conduction electrons or electrons, the collision rate of conduction electrons with the lattice atoms, oscillating lattice atoms or ions increases, because they want the explanation in terms of the movement of the conduction electrons. So this is what is happening. So the collision rate of conduction electrons increases. That means it is difficult for them to pass through. So as the collision rate increases, what can happen? This this can increase the resistance, or we can say that, so the resistance is increasing means rate of increase of current decreases. So as the collision rate increases, rate of increase of current decreases with the with the an increase in PD. See, PD is continuously increasing, but along with the PD, initially we see that as the PD increases, the current is increasing, but later on, because of this heating effect and development of temperature and all, the rate of increase of current decreases with an increase in PD, or in another way we can say that the increase in PD is at a greater rate, at a faster rate than increase in current. This is what we see in the graph. Initially current and voltage are increasing with the voltage current increases, but after that, that rate of increase of current is not increasing like the increase in PD. So increase in PD is faster rate. Now let's see what is happening in a thermistor. What is happening in a thermistor? And as you know, the thermistors are made from semiconductor materials. Semiconductors. Thermistors are made from semiconductors. So in this thermistor graph also you can see that initially as the voltage increases, the current is increasing. So initially as voltage increases, current increases, and due to the heating effect, due to heating effect of current, temperature increases. But here as the temperature increases, more conduction electrons are produced by thermionic emission. That is the difference, because thermistors are made from semiconductor materials. So semiconductor materials, there are covalent bonds. So as the semiconductor material gains heat energy from the temperature, or as the temperature increases, more and more covalent bonds break open and more electrons become free. So this is what is the meaning of saying that thermionic emission. So let us write, due to the heating effect of current, temperature increases. This causes more conduction electrons to be produced. This causes more conduction electrons. This is by thermionic emission. So more number of conduction electrons are produced. Electrons to be produced, thermionic emission from semiconductor material. So more conduction electrons are produced means the current increases. As conduction electrons increases, current increases, or resistance of thermistor decreases. So as a conclusion, we can say that as temperature increases, resistance of thermistor decreases. So having a negative temperature coefficient. This is the meaning of saying that they have negative temperature coefficient. So just draw the circuit diagram only. The wire is given. So you have to include an ammeter, a voltmeter, a variable resistor, and of course we need a battery source also. So let us start with the battery source. Let us give the battery here. Then we need an ammeter to measure the current. This is the wire. Then we can use a variable resistor to control the current through the circuit. So let us complete that part. Then of course we need a voltmeter to measure the voltage across the nichrome wire. So connect a voltmeter parallel to the nichrome wire. So this is the experimental arrangement. Now there is a graph given here, a graph of potential difference, voltage and length. Now the question is, determine the resistivity of the nichrome. So we have to calculate the resistivity of the nichrome. So we have an equation for resistivity in terms of resistance. Resistance is rho L over A. This is the equation you studied. But here length is given, voltage is given, nothing is mentioned about the area of the nichrome wire. But it says that for each length she measured the potential difference across the nichrome wire. She used the variable resistor to keep the current in the wire. So she keep the current is also the same. So this is the current. She made a fixed current. So from the graph, what we can calculate is just the gradient. So we know that the gradient from this graph, the gradient, which is delta y over delta x. So y-axis is the potential axis. So the gradient is just coming, it has a ratio of v over L. This is what the gradient we are getting from this graph. But it also says that there is a current. So the gradient, it is v over L. And also there is one more information given. See, this information we already know. R is rho L by A. But this R, which is V over I, which is rho L by A. So using this, we can calculate the resistivity. So I'm going to start from this relation, that is V over I equals V over I equals rho L over A. See, this V over I is nothing but it is a resistance. So from this, let us write an equation for resistance. It is V over I times A over L, or we can rearrange and write it as V over L times A by I. Actually, this V over L only we are getting it as the gradient. So from this we can write rho is gradient times A over I. This is the way we can calculate the resistivity. Resistivity is the gradient times A over I. See, the gradient what we are getting is V over L. So we can calculate the gradient and multiply that with the A over L. See, it is gradient is V over L. So we have V over I equals rho L over A. From that, the gradient is rho IL over VA, but V over L, we are arranging it and writing it A over I. So rho is equal to gradient times A over I. So now let us calculate how much is the gradient. Gradient is V over L. So from the graph, we can consider the first point and the last point. So the first point is it's 1 and 4 point. So this is 4.15. It is coming approximately 4.15. 4.15. This is the coordinate. So from this, we can calculate the gradient. So I'm calculating the gradient here. The gradient equals delta y by delta x, which is 4.15 minus 0, which is 4.15, and the x-axis is 1. So we are getting the gradient as 4.15. This is the gradient we are getting. So it is volt per meter. This is the gradient. Now let's use this gradient. Let's use this gradient here. So we have place here to continue. So this is equal to 4.15 times the area. What is the area given? The area, cross-sectional area of nichrome wire, it is given here, which is 5.3. So this is 5.31 times 10 to the power of negative 8 over the current. Current is given in the first part. It is 0.20 amps. So the current is 0.20 amps. So on calculation, we are getting an answer of 1.1 times 10 to the power of negative 6, 1.10 times 10 to the power of negative 6 ohm meter. This is the resistivity from the graph for the nichrome wire. So let us see from the beginning. So a voltage length graph is given. So from that, what we can calculate from the graph is the gradient, which is delta y by delta x. So we calculated here as V over L. So gradient is V over L. And also we know that R is rho L over A or V over I is rho L over A. Now, using that relation, we are starting here. R is equal to rho L over A or V over I is rho L over A, and we are rearranging, taking rho as the subject and rearranging, and V over L we are bringing together as the gradient. Now also we are calculating the gradient and substituting all the values, we are getting an answer of 1.1 10 to the power of negative 6 ohm meter. Then let us move on to the next part of the question. Calculate the power dissipated from the nichrome wire to the surrounding when the length of the wire is 0.75. So calculate the power dissipated. So we can use the equation for power dissipation. It is V times I. When the nichrome wire has a length of, so it has a length of 0.75 meter. So let us see for a 0.75 meter length, where is 0.75? So from the graph, 0.75, it is between 7 and 8. Correspondingly, we are getting a voltage of, this is the voltage we are getting. Correspondingly, we are getting a voltage of 3.1 volt. Approximately 3.1 volt we are getting, 3.1 volt. So, for a length of 0.75, we are getting an approximately value of voltage 3.1. So, I am writing here from graph. So, we can write from graph at length equals 0.75 meter, voltage is 3.1 volt. So let us bring it here. So it is 3.1 times, already given in the question, there is a current of 0.20. So altogether, we are getting an answer of 0.62 watts, approximately 0.62 watts. This is what we are getting, the power dissipated for a length of 0.75 meter of wire. Now we are moved on to the next question. Two copper wires W and Z are joined in such a way that, or the condition given is, wire W has twice the diameter of wire Z. It has twice the diameter. Now the first part of the question is, state the purpose of the resistor in the circuit. So the resistor is used in the circuit to control the current in the circuit or to avoid overheating. So let us write the answer. Resistor is used to control, resist or to control the circuit current. Okay. Also to avoid overheating. overheating of the circuit or overheating of the wires here. Now, the current in the conductor is given by, there is an equation. Complete the following table which shows the ratios of quantities of wires W and Z. The first row has been completed for you. The first row says the ratio of electron density, conduction electron density of wire W to wire Z is 1 because both the wires are made of same material. So since it is same material, the number density is the same. So number density in wire W is same as number density in wire Z. So the value is 1. The same way, what is the ratio of current in W to current in Z? So let us go and see. It's very obvious that W and Z, these two wires are connected in series. So the same current is flowing through them. Okay, same current starting from the cell. Here the current is IW. The same current is IW, which is equal to the current flowing through the Z wire because they are connected in series. So we can say that the value will be, so let us write the justification first of all. Okay, I W is equal to I Z as both are connected in series. So since both are equal, the ratio will be 1. Then let us see the ratio of the voltages VW and VZ. Okay, so for that it says that, so I am writing the calculation here. It says that the resistance of Z, it is only half of the resistance of W. I mean the diameter, not the resistance, sorry, the diameter. Therefore, the radius of Z is only half of the radius of wire W. It's already given here. Look at the diameters. Diameter of Z is half of the diameter of W. Therefore, the radius Z is half of radius W. So since the radius is, so this is the radius, okay, radius. Okay, I'm starting with the radius. So since the radius is given, we can calculate what is the area of W. Area of W is pi r W the whole square, and area of Z is pi half r W the whole square, because the radius of Z is half the radius of W. So instead of RZ, I substituted half the radius of RW the whole square. So this is the areas we are getting. So this is equal to 1 by 4 pi RW square. So AZ is 1 by 4 pi RW square. Now let me come to this place, and we know that radius is inversely proportional to area. So using this idea, that is radius of wire is Z, see radius and A are inversely proportional. So AZ is only 1/4 of the area of AW. So I can write that also here. that is AZ is only 1/4 of AW. AZ is only 1/4 of AW. So from this we can write, so from here, so I'm coming from here, therefore RZ will be 4 times RW, because R and A are inversely proportional. R and A are inversely proportional, and we found that area of Z is 1/4 of area of W. That means R of Z will be reciprocal of 1/4, 4 times R of W. Since resistance and voltages are directly proportional because it's a fixed resistor, we can say that the voltage of Z is 4 times the voltage of W, because V is equal to I times R. This is Ohm's law relation. As R increases, voltage is also increases. So we see the relation that Vz is 4 times Vw. So let us use that here. If Vw is so here we can write a ratio. Let us write it here itself. Vw by Vz is 1/4. This is the ratio we are getting. So we are getting it as 1/4. The reason, there is no place here to write, so that is why I wrote all the reason here, starting with the radius. Radius, diameter is, Z is half of diameter of RW, so radius is half. Therefore, area of W, RW square, area of Z is half of RW square, and finally we got it as 1/4 AW. Then we are coming to the relation R and A are inversely proportional. So from that we are getting RZ is 4 times RW. Similarly, VZ is 4 times VW. So we are getting a ratio VW by VZ is 1/4. Okay. So this is what is getting here. So I will just write the reason briefly here. I can say R, sorry, resistance of Z is 1/2 resistance of W. Resistance, not the resistance, it is a radius. So from this we can write area is 1/4 of AW. From that we can write resistance of Z is 4 times resistance of W. So Vz is 4 times Vw. This is the reason. Other things I have just shown you all the steps, but when you are writing the reason, you can write this much. Now we are coming to the next question. The circuit diagram shows a resistor of resistance 270 connected to a battery of EMF 9 volt. The battery has an internal resistance of 15 ohms. The question is, explain why the reading on the voltmeter is less than 9 volt when the switch is closed. Okay, so it is given the EMF, it is given the resistance of the load resistor, the internal resistance, everything it is given. It says it has an internal resistance of 15 ohms. So here the internal resistance is coming as 15 ohms. Here it is 270, EMF is 9 volt, all these things are provided. Explain why the reading on the voltmeter is less than 9 volt, reading on the voltmeter. So first of all, let us see what is the current flowing or starting from the EMF. So current is EMF over R total, which is 9 over total resistance is 270 plus 50. So we are getting a current of 0.031 amps. This is the circuit current flowing. Therefore, this voltmeter is connected across. Actually, this voltmeter is giving the drop across this resistor VR. This voltmeter is giving VR only. So, VR is I times the R value, which is 0.031 times R value is 270. On calculation, it is giving an answer of 8.53 volts, which is less than 9 volt. Explain why the reading on the voltmeter is less than. This is the value we are getting. In fact, this will come as the calculate the reading on the voltmeter. So, in fact, this will come as the calculation here, and I'm going to write the answer for explain why the reading on the voltmeter is less than. So, this is my A part and this is my B part. Okay. So, A part I have done it here. Calculate the reading. Now, explain. What is the explanation? Explain. Explain why this is happening. See, the PD is the energy transferred per the unit charge. Okay, this is the meaning of PD. PD is the energy transferred per unit charge. So when switch is closed, a current is flowing through the cell, and some energy is lost in the internal resistance. Actually, this is a reason. Some energy is lost in the internal resistance. And this energy, we call it as the lost volt. Lost volt. In the lost volt in the internal resistance. So only the balance voltage is dropped across the rest of the circuit. Only the balance voltage is dropped across the rest of the circuit. So PD is the energy transferred for a unit charge. When switch is closed, a current is flowing through the cell and some energy is lost in the internal resistance as lost volt in the internal resistance. Only the balance voltage is dropped across the rest of the circuit. Now, let us see the next part. The switch remains closed and 12 coulomb of charge flows through the battery. Calculate the decrease in the chemical energy store of the battery. You have studied that PD or voltage, it is the energy transferred by unit charge. So, that means energy transferred. Energy transferred by unit charge. So, energy equals V times Q. And when switch remains closed and 12 coulomb of charges flow through the battery, so the charge of the voltage of the battery is 9 and there is a charge of 12 coulombs. So it is 12, which is giving an answer of 108 joules. This is the chemical energy store of the battery, the decrease in the chemical energy store of the battery. Now we are coming to the last question. The student connected the circuit shown. The battery has a negligible internal resistance. The graph shows how the resistance of the thermistor varies with the temperature. Because it's a thermistor circuit. Determine the temperature of the circuit. The reading on the voltmeter is when the reading on the voltmeter is 3.42 volt, determine the temperature of the thermistor. This is the question. Okay, so let's see the circuit. So there is a thermistor, there is a fixed resistor, the EMF is given. Now the question is, the graph shows the resistance of the thermistor, how it varies with the temperature. The reading on the voltmeter is 3.42 volt, determine the temperature of the thermistor. So reading on the voltmeter is 3.42. So where is the voltmeter connected? The voltmeter is connected across a resistor. So what is given here is VR, the drop across the resistor, which is 3.42. 3.42. This is 3.42 volt. Therefore, we can calculate what is the current. So this is the current starting from the battery source I, but the same current is flowing through the resistor as IR. The resistor is given, the voltage is given, therefore we can calculate what is this IR. So let us calculate that current first. IR equals the voltage of the resistor over the resistance, which is 3.42 over the resistance is given as 11.5 and we are getting a current of 0.297 amps. This is the current passing through IR. Then we can see that IR, current through IR and current through the thermistor, they are connected in series, which is 0.297 amps because they are connected in series. As they are in series, the same current is flowing. Therefore, we can calculate what is the current flowing through the thermistor, which is 2.9, and we can calculate what is the voltage of resistance of the thermistor. we can see the resistance of the thermistor. So voltage of the thermistor equals I thermistor times resistance of thermistor. Therefore, let us calculate what is the resistance of the thermistor. So R of thermistor. R of thermistor equals voltage over the corresponding current. The voltage across the resistor is 3.42. Therefore, the voltage across the thermistor, total it is 9 volt. We know the current, so we can calculate what is the so let us see, the voltage of the thermistor will be 9 minus the voltage of the resistor, which is 3.42. This is the voltage of the thermistor over the current of the thermistor, which is 297, and this will give an answer of approximately 18.8 ohms or approximately 19 ohms. Now let's see what is the temperature for 19 ohm resistance. Where is 19 ohm resistor? So the 19 ohm resistor is coming this side. 19 less than, so each division is 2, so it is 12, 14, 16, 18, so 19 here. Let us draw a line to the graph and take the corresponding temperature. So the corresponding temperature is coming as 32, 34. So this is giving a current of this, giving a temperature of 32. And this is giving a resistance of 90. So the answer is, from graph, temperature corresponds to 19 ohm resistor equals 34 degree centigrade. So this is the temperature. Now the next one is the student suggests that if the EMF of the battery is double, the reading on the voltmeter will double. This is whether a student suggestion is correct. The student suggests that the EMF of the battery is doubled. So when EMF is increased, definitely the current will increase. When the current increases, there will be a heating effect. We have seen it in the previous questions. So temperature increases. So resistance of the LDR decreases. Therefore, drop across the LDR decreases. So let us write it step by step. When EMF increases, what is happening? I current increases, which causes a heating effect. And temperature increases. Now we can see that as temperature increases, the resistance of the thermistor decreases, because we know that there is a relation, resistance of thermistor is inversely proportional to the temperature. So this relation. So resistance of thermistor decreases. And when resistance of the thermistor decreases, so the voltage of the thermistor decreases as I is the same. And when the voltage of the thermistor decreases, this makes voltage across fixed fixed resistor to increase more than double the value. So student is incorrect. So the student is incorrect because the variation of resistance and temperature is not having a linear relationship. It's a non-linear relationship only. Temperature and resistance. It's a non-linear relationship. So when the temperature decreases, we cannot say that the voltage of the thermistor decreases by the same amount. Accordingly, we cannot say that the voltage of the fixed resistor increases uh, proportionally. So the student is incorrect.